Good morning, everybody. I hope you enjoy, or you are enjoying SIBGRAPI 2021. This is tutorial number 3. The title of the tutorial is Neural Networks for Implicit Representations of 3D Scenes. The authors are from PUC-Rio and IMPA. The authors are Luiz, Guilherme, Vinícius, Professor Hélio Lopes, Tiago, Daniel, Thales, Alisson, and Professor Luiz Velho. Professor Hélio will start the presentation, and after his presentation, we'll have the complete tutorial in video. I hope you enjoyed this tutorial.
Good morning, everyone. Welcome to SIBGRAPI 2021. In particular to this tutorial that the name is Neural Networks for Presentation of 3D Scenes. As you can observe, deep neural networks has gained a lot of importance in the last few years, in particular to the computer graphics community. And this tutorial has the aim to bring these new concepts of deep neural networks to computer graphics and discuss and motivate all the students and the participants to study this new area. So our tutorial will be divided in 2 parts. In the first part, we will talk about the first and second generation models of this new technology. And the second part will bring the third and fourth generation models. So for each part, we produced a video that will be played in the sequence. Thank you very much. Enjoy our course and have a nice day. So we can play now the video. Thank you very much.
So continuing the tutorial Neural Networks for Implicit Representation of 3D Scenes for SIBGRAPI 2021. I'm Vinícius da Silva, and I'll be presenting Occupancy Networks, Learning 3D Reconstruction in Function Space. This is one of the first papers to present this idea of using implicit models that are represented by trained neural networks. The idea is quite simple, actually. The implicit representation is just an occupancy value. So the idea of the networks to provide the probability of occupancy that as a given 3D point in the space has. So a probability near 1 means that the point is probably inside the object, and the probability near 0 means the opposite. So we have a function f that has trainable parameters theta, and our domain is first there are 3, so we have 3D points as input, and also we have a condition that it can be an image or point cloud or volume. This condition is used for generalizing the model, so it can actually infer from models that aren't seen before. And the result is just this occupancy probability value. Quite simple, the idea. And this work was concurrent with 2 other works in CVPR 2019. First is DeepSDF, and the second is IMNet. It's important that see that DeepSDF is a method for representing through a sign distance function, which is different from this occupancy approach here. So let's talk about the network architecture now. We will divide the architecture in a few parts that are important for understanding. First, we have the part that's related with the conditioning of the input. And this is quite simple. We just have an encoder, and this encoder provides a code C based on the input. And this encoder can be used with a conjunction of several auxiliary networks, such as a 3D convolutional neural network. If you have a volumetric input, a volume of voxels, a point net if you have a point cloud input, and a ResNet 18 if you have just images. This is the first part of the network. Then we have another part that is actually the input that we'll be using for inference, which is a set of n 3D points, and our objective is to calculate the occupancy probability of those 3D points. And the usual layers setup for this architecture is a layer with 256 neurons, and this is used for all parts of the network. Then we have the main part which is a loop that use ResNet with conditional batch normalization. This loop runs from 1 to 5, so 5 iterations of this loop. I will not consider that the public knows what ResNet and conditional batch normalization is, so we just make a parenthesis here now to understand those concepts, and then we get to do that discussion later on, so we have the concepts more established afterwards. So what is conditional batch normalization? Usual batch normalization is a way to to ease the covariate shift, which is a problem that can make your gradients work in weird ways when you are training. So this is just a normalization, and you normalize based on your the distribution of your inputs. So you from your distribution of 3D points, in our case, you just use the mean of that distribution and the standard deviation. And then you can normalize your input and minimize this problem. In conditional batch normalization, we will have additional parameters, which are the parameters that are used for conditioning. In this case, is the gamma and this beta, and they are dependent of the code that was generated by our conditioning inputs, the images, volumes, or point clouds. The computation is also simple. We have our input, and we just make the usual batch normalization. So we just center based on the mean, and scale based on the standard deviation. Then we apply the conditional batch normalization, which is another scaling with also one bias that is dependent of the conditioning code C, and both beta and gamma are conditioned to this code C. Alright, so now that we already know how we normalize our data, we can talk about the main block of learning that the network has, which is the ResNet block. And actually, it's also a quite simple idea. You just have, this is just a block that you have a skip connection that is the identity. So, for example, if you train something that is near your identity, you can just use this skip connection and the training will be much easier. And however, instead of training your desired function f of x, you are actually training for f of x plus x. And this works because of a few mathematical properties that come from strong mathematical concepts such as wavelets, which also operates on this residual way, but I don't have time to make a deep discussion about that, but by intuition you can see that this approach works because of those mathematical properties that come from wavelets. So since we are not training our desired function of f of x, we just need to make a subtraction of x so you can have your desired function. Now that we have those concepts and we know them, we can actually understand the main block of this network architecture. First, we have our beta and gamma for conditional batch normalization that are dependent on our code C generated by the encoder, and those parameters are passed for the conditional batch normalization in conjunction with the input points. And then this importance block has two of those layers used in this network, and this is the ResNet residual part that has this skip connection. Then the network architecture has an additional layer with 256 neurons. Then after this loop from 1 to 5, you have an additional conditional batch normalization, which is done in the same way as before. And then in the end, you have a fully connected projection followed by a sigmoid. So you can have an output that is 1 for each, that has size 1 for each of the input points, and also is a probability from 0 to 1 since you are applying sigmoid. So now that we know how the network works, we can talk a little bit about the training. This is the equation they use for training, and it has a usual training term and also a generative term. So we have the theta parameters that are the network parameters, and we have the psi, which are the generative parameters, if you want to use this network in a generative setup. So this term here, this summation here is just the summation on mini batches. So you have a specific number of mini batches that you want to train. Then this is the most important term, the supervised loss. We actually have the function f with the learnable parameters, and this function receives the points and the conditioning codes. and then we have ground truths occupancy that are used for the training. Then we have the generative term, which uses an additional encoder Q of psi that generates a code Z based on the points and the ground truth occupancies, and it compares with the code that's generated for the points, and this comparison is done using the Kullback library divergence. More specifically, they use K randomly sampled points with K equals to 2048, and for the loss function they use the binary cross entropy loss, and the Q of psi is the encoder that they use. Okay, after you have the trained network, you can actually compute the occupancy for your entire space. So if you want to render and visualize the model, you can use this multi-resolution isosurface extraction. And this is actually also quite simple. It's just a matter of building an octree. So you evaluate voxel grid points for occupancy, and then you subdivide for defining several levels of the octree. Then you can just use Marsh cubes to extract a mesh and visualize. Okay, so this is the paper. Thank you for your attention, and the tutorial will continue with the next paper.
I will present DeepSDF, Learning Continual Signed Distance Functions for Shape Representation, by Park and others, published in 2019. I will first talk briefly about the problem statement and some key concepts necessary to understand the work, and then I will present the approach proposed by Park to try and solve this problem. We assume that a 3D object is represented implicitly by a function f. More specifically, f is a signed distance function. We also assume that we don't know f nor anything about the object itself. So, given only point samples and their corresponding function values, how can we approximate the function f and eventually reconstruct the original object? Some key concepts to understand the problem better. We wish to estimate the object's shape given only point samples. More formally, given a set of x points in our tree, and their function values s as scalars, we wish to estimate f and find its zero-level set, which is the object's surface itself. One of the key ideas to approach this problem is built upon the universal approximation theorem that states that multilayer perceptrons or feed-forward networks are function estimators, and then they can approximate functions of an arbitrary precision given that they have an infinite number of nodes. However, since we do not have the computational power to handle an infinite number of nodes, we can approximate a function well enough using a finite number of nodes and layers. Given points in the domain and their associated values, we can simply estimate an unknown function by training a neural network using the universal approximation theorem. From this trained network, it is possible to create a series of samples in the function domain, which we assume here conform -1 to 1 in the tree axis. And then we can calculate an approximation of their function values using this network. The object that we wish to reconstruct can then be obtained by using a simple interpolation method of the zero-level set of F. Here's a more graphical example where on the left we have a plane from the ShapeNet dataset, ShapeNet version 2 dataset. Then we sample this plane densely, both outside and inside the surface. Here I'm only showing the samples inside the surface for better understanding. And then we feed these samples to a neural network that will try and regress the SDF value for each sample. After training this network for a certain number of epochs, we may be able to sample again the functions domain and then reconstruct and then estimate the F value for each sample and then reconstruct eventually an approximation of the input object. It's shown here on the right using Martian cubes. There are a series of advantages when employing this kind of method. One of them is that there is no need to discretize a domain. We are able to learn a continuous function over the whole domain, compared to other techniques where we need to voxelize the domain one way or another, or we learn the representation directly from the mesh itself. All right. Another advantage is that this is not modeled as a classification problem, but as a regression one. A classification problem, such as occupancy networks, where the points are classified as inside or outside the function. We actually try to solve a regression problem, where we have a series of samples of a given function, and we wish to create another function that best approximates that function that we target. Okay. As a side note, the sample class is implicitly defined by its signal. However, there are also problems with this approach. The most grave problem is that a single network may estimate only one function, meaning basically that a network encodes a single object only. There is no generalization capability. I cannot use one network to try and estimate another function. It makes sense, since the model is overfitted from its inception. This overfit is intended in order to estimate the zero-level set of this function better. Okay? However, then comes the question, how can we adapt the network to learn a family of functions instead of learning a single function at a time? Park and others propose the addition of a latent vector in order to encode the particular shape as an input to the network. And they propose an autodecoder architecture for shape family learning. Instead of training a feed-forward model to learn only a single shape, now we train as the same model to learn a family of shapes, such as a family of planes, chairs, sofas, etc. Class of objects instead of a single one. More formally, now our function f receives as input the latent vector z for function I and as sample in R3. This approximates the SDF of the ith object given that sample x in R3. More graphically, instead of passing only the point sample as input to the network, now we also pass the latent code for that particular object as input. The network then tries to find the best code to optimize this. A side-by-side comparison retrieved on the work of Park et al. Our original approach is to simply train a model using only the point sample, XYZ, fed into the network, resulting in an SDF value. This is then the loss factor is calculated, and then there is the backpropagation process. The weights of the network are adjusted. Now, Park's proposal is simply to append to this point sample a latent vector encoding which function we are currently learning. Thus, we are able to simply change the code in order to change the function, change the object being learned as well. A graphical representation of the architecture proposed by Park is presented here. The architecture is fairly simple. There are only 8 layers, or 8 fully connected layers with very little nonlinearities. Each layer presents 512 nodes, okay, with the exception of the last layer that the output is a single node, which is the SDF value. As input, the XYZ coordinates of the sample is concatenated to the latent vector, which here is assumed to have 256 positions. This is fed into the network, and then there is a skip connection to the 4th layer. Park explains that this enabled better results for deeper networks, such as this one with 8 layers. This result is then fed into the network, and at the last layer, a hyperbolic tangent nonlinearity is applied to the result in order to obtain the SDF value. With this proposal, Park is able to fetch a series of planes. For instance, here I fetched 3 random planes from the ShapeNet class, ShapeNet dataset, sampled them densely here. As before, I'm showing only the internal samples, and then I can use them as input to the DeepSDF network. This enables us with a single network to learn not only one plane as before, but as a family of planes. Okay. Now I'll show some results of DeepSDF for a single plane, for instance. Here on the middle we have the original ShapeNet plane, okay, used to sample the data, and then surrounding it we have the results from DeepSDF at different epochs. After 100 epochs of training, 500 epochs of training, 1,000 epochs of training, and 2,000 epochs of training. In their article, Park used 1,000 epochs to report the results, but the code in the repository uses 2,000 epochs. So here at 100 epochs, we can already see that the outline of the plane is already fairly well defined. There is very poor, but there is a definition. Here we can see that the outline of the plane is already fairly well defined at 100 epochs. We can already identify the 2 turbines here under the wings, a part of the fuel tanks. I assume they are the fuel tanks, but there are no other details such as the tail here, or the landing gear, nor the antenna, or anything else. At 500 epochs of training, we can already identify a piece of the landing gear here under the left wing. The fuel tanks and turbines are better defined already, part of the tail as well, but no antenna yet. At 100 epochs, it seems that there were some details added to the wings especially, but the tail is a little bit worse. And at 2,000 epochs, we can see that the outline of the plane is satisfactory, basically, when compared to the original ShapeNet plane. During our experiments, we noticed that that DeepSDF has some issues representing thin objects, such as the antenna here. Well, this is fairly expected to this point because it's very difficult to actually sample points inside this antenna. If you sample uniformly at random in the domain, the probability of a single sample falling here in this region is very, very small. So it's very difficult to actually reconstruct thin objects like this. You can also observe a similar effect here on the landing gear. especially at 2000 epochs, we can see that the landing gear strut is not present. So basically, even though the wheels of the landing gear are fairly well defined, especially the ridge between both tires, the landing strut is not defined here, so the gear is basically floating compared to the model. Okay. Now, for the next example, we have an object of the lamp class. Same disposition as before. In the middle, we have the ShapeNet object, and then we have the objects reconstructed after 100 epochs of training, 500, 1000, and 2000 epochs of training. This object in particular is very challenging for the DeepSDF to reconstruct because it goes against the recommendation of the authors that the objects be watertight. This object is not watertight, it's not closed. The top of the lamp here and the bottom of it are actually open. So the internal area of the object, there is basically no internal volume of the object if you analyze it. There is only this area surface here of this lamp, so it's very, very difficult for DeepSDF to actually approximate this very well. At 100 epochs, we can see that the general outline of the lamp is actually good, albeit a bit wobbly, but it represents a lamp. However, at 500 epochs, we see the problem with the sampling here, the fact that this is an open object, that it seems that the lamp has been torn open. DeepSDF was not able to accurately reconstruct the top of the lamp here. This is partially fixed at 1000 epochs, although there are some holes in the lamp that we can see here. Okay, but there are already details on this bead at the top of the lamp here if we compare to the original model. Okay, so even though this is a very challenging model for DeepSDF to accurately reconstruct, we can see that even so it's able to capture some detail of the underlying function. At 2000 epochs, we can see that the results have progressed pretty well compared to the 500 epoch result, but it remains very similar to the results of 1000 epochs, as we can see here side by side. Okay. This is a result obtained directly from Park's work, not our experiments. We can see here the results for the chairs dataset. On the right of each model, we see the ShapeNet dataset, okay, and on the left, the DeepSDF reconstruction of that same model. This is trained on a single model, on a single neural network, meaning basically that all of these shares were fed to a single neural network, and then this network was used to reconstruct every single one of them. We can see here that DeepSDF DeepSDF is able to capture some thin structures from this share, for instance, its arms and its support, really. And it's also able to correct some things with the original model. Here we can see that the original ShapeNet model has a very low polygon count. Now DeepSDF is able to overcome this. Okay, if we look at here, we don't see a low polygon count or any kind of polygonization of the output model. We see that it kind of smooths the model here. It may lose some detail, right, but it reconstructs the original model very closely. Even the sofa's legs here, okay. On the bottom left, we can see a similar result where this share, quite possibly due to illumination, but also due to low polygon count, is reconstructed in a more smooth manner. We are not able to see these faces here, these stripes from the original model. Okay. However, on the bottom right, we can see that DeepSDF does have some problems with certain kinds of objects. For instance, we can see here that this is actually a two-object model, so it's not only the chair but also the footrest. Okay, DeepSDF is not able to accurately reconstruct both of the supports, from both the chair and the footrest in this case. However, the seat and the footrests have an okay reconstruction. Not perfect, but also not terrible. Okay. Some concluding remarks about DeepSDF. One of the most important results is that DeepSDF is able to generate a continuous approximation of signed distance functions compared to, as opposed actually to other approaches at the time that mostly discretized the input domain in some manner, usually by simple voxelization. Okay, so DeepSDF was, at our knowledge, one of the only ones that proposed a continuous representation at the time. Also, it was able to learn a family of signed distance functions, not only one signed distance function for each model, but each model is able to encode a family of signed distance functions. Okay, and one of the results that we did not mention here on this presentation is that DeepSDF is also able to infer the shape given only partial observations. So we don't need to sample the domain at inference time very densely. We can provide a snapshot with few samples, and DeepSDF is able to reconstruct the original model from that. With that, thank you very much for watching this presentation.
Hi, my name is Thiago Novelo de Brito, and in this talk we are going to present ConvexNet and BSP-Net. These neural networks are capable of representing regions of the space as union of convex shapes. For this task, they use construct solid geometry on their function representations. These networks were presented at CVPR 2020 by Deng et al. And Chen et al. Respectively. These neural networks encode simple CSG trees into a kind of neural implicit function that represents the union of convex bodies, where these convex are given by half-space intersections. Before we introduce ConvexNet and BSP-Net, let us explain what we mean by learning an implicit function using neural networks. This was probably presented in the previous lectures. However, I think it is very important to remember the concept here. We consider the dataset to be a set of pairs Mi or I, where Mi are the inputs that can be images, point clouds, or voxel grids, for example. Oi are the corresponding indicator functions of the inputs. The object surface is represented by the 0.5 level set of the indicator function. The points with values less than 0.5 indicates that they are outside the region, and the points for which the function is greater than 0.5 indicates that we are inside the region. Now, note that we are considering a kind of continuous indicator function. This is because we are dealing with neural networks, which are usually continuous functions. Now, let f be an unknown function with domain in the three-dimensional space Cartesian with the input domain. This function must be an indicator function when restricted to an input. This is a requirement. We also require that for each pair mi or I in the dataset, the function restricted to mi must coincide with the indicator function I. Next, we define a neural network and train its parameters such that it approximates the function f. This network basically considers a encoder that receives the input object and returns a feature code that is which is the input of a decoder. The output of this decoder is a list of parameters used to construct a indicator function. ConvexNet and BSP-Net, the neural networks that we are going to present, are two neural network architectures that defines the indicator function using construct solid geometry. Finally, after we train the network, given an unknown input, we have a new indicator function for this input. Well, again, the neural networks that we are going to present in this talk consider construct solid geometry in their structures. So let's briefly present this concept. In CSG, Boolean operators like union, intersection, the difference are used to combine simple objects to create complex ones. CSG objects can be represented by trees. The leaves corresponds to primitives like half space, cubes, balls, cylinders, and the nodes represent operations. See the figure on the right, for example. A CSG object can be modeled using an implicit function. The leaves are simple implicit functions, which we call the primitives, and nodes are operation between its child nodes. Observe these operations could include union, intersection, and difference, for example. The union of two functions can be defined by the minimum between them. The intersection of two functions is defined by the maximum between the functions, and the difference of two functions is the maximum between the first one and the negative of the second one. ConvexNet and BSP-Net are neural networks that encode simple CSG trees. The leaves will be just half spaces. An estimated layer will consider the intersection of half space to form convex shapes. And finally, the root of the tree is obtained through a union operator that groups the convex shapes into a single shape. We now present ConvexNet, a network capable of representing a finite family of shapes. This family is automatically derived via a autoencoding process. Specifically, ConvexNet learns for each input a function which is an indicator function that represents a union of convex shapes. These convex are given by intersections between half spaces. In other words, it represents a simple fixed CSG tree. Again, the leaves are half space, the intermediate nodes are intersections, and the root is the union. Let's see how these networks operates. Given input M, an encoder-decoder estimates the parameters of the planes, the pairs of betas and t's. Betas are a collection of half spaces parameters used to construct the convexes, and t's are the convex positions. Each t corresponds to an origin of a convex object. Therefore, the desired indicator function is then given by taking the maximum of the indicator function of the convexes. Let us understand this network by looking at a single convex. That is, we look at a piece of the network which corresponds to an intermediate node of the underlying CSG tree. First, we consider the problem of representing a smooth convex using half-space intersections. The side and distance function of a single plane can be modeled using the dot product between a vector n and the input point plus a number d, where n is the unit normal vector of the plane and d is the plane offset, that is the distance from the plane to the space origin. Given a collection of side and distance functions of the planes, we use the maximum of them to define the side and distance functions of the boundary of the intersection of the corresponding half spaces. However, the maximum function is not differentiable. Therefore, we consider a smooth approximation using the logarithm of the summation of the exponentials. The parameter delta controls the smoothness of the resulting convex. The resulting function is not an indicator function. In fact, it is an approximation of a side and distance function. The author used the sigmoid functions to convert the side and distance function into a smooth indicator function. Therefore, the resulting functions represent the approximation of the indicator function of the smooth convex. The parameter sigma controls the sharpness of the transition of the indicator function. Let's construct a single convex autoencoder. This will be responsible to learn a single convex shape. Given an input, which can be an image, for example, the encoder derives a feature called lambda. And then an decoder receives this feature code and returns a collection of hyperplane parameters. The corresponding half space are intersected in order to create a smooth convex shape. This is done using the procedure given in the previous slide. Here, beta is the set of all of the plane parameters and the smoothness parameters. Finally, the neural network of a single convex is extended to encode union of convexes. Again, the encoder outputs a feature called lambda, which represents the convex shapes. Note that here we are considering a collection of convex shapes. In other words, we are extending the network presented at the previous slide. The feature vector lambda is the input of the decoder, which returns a collection of parameters, which are denoted by beta. Each beta corresponds to a parameter, to the parameters of the half space used to define a convex shape. The last pass of this network consists of grouping these convexes into a single object. It is very important to note that the CSG tree encoded in this network representation is fixed. Therefore, we have to choose the number of convex used to construct each convex shape. ConvexNet can be trained using the expected square loss function. Given a batch of queries of points, the network predicts the corresponding indicator function. Then the gradients are backpropagated in order to approximate the predicted indicator function with the corresponding ground truth. In other words, the gradient descent is used. Also, other losses are used in order to help the convergence and quality of the underlying CSG object. They minimize the number of intersections between the convex shape, and they also force each convex to have a unique origin position. We now present the BSP-Net, which is very similar to ConvexNet, since it also learns a simple CSG object. However, the CSG tree is fixed in the ConvexNet representation, and here it will be possible to learn the connection between half space and convexes. Specifically, given an input M, BSP-Net learns a CSG indicator function where a collection of planes imply in a binary partition of the space. This is very similar to ConvexNet case. However, here there is an operator that groups this half space to create a collection of convex shapes using the intersection operator. This is new in relation to ConvexNet. This operator learns the edge that connects the half space nodes to the convex nodes. Finally, as expected, the convex shapes are merged to produce the indicator function using the union operator. The entire process is based on CCG operations, hence the input shapes can be easily represented using polygonal mesh. We show how the CSG tree is represented in a single in the network. This is the BSP-Net architecture. Given a voxel model or an image, BSP-Net uses an encoder to create a feature code. Then a decoder, which is a multilayer perceptron, maps the feature code to a plane to the plane parameters, which are the leaves nodes or on the CSG tree. The plane parameters define its implicit equations. Then it is sampled a collection of points in the space. Here, as you can see, we are using homogeneous coordinates. These points were evaluated in the half space function using the products between the points and the plane parameters. Again, this is very similar to the ConvexNet. I just apologize for the different notations. As a result, we obtain the signed distance of these points to the corresponding planes. This can be visualized as the first layer of the CSG tree. To represent the connection between the half space and the convex shape, BSP-Net uses a trainable binary matrix. This gives the signed distance of the collection of points of the boundary of the resulting convex shapes. Finally, auxiliary weights are considered in the weighted sum to obtain the resulting shape, which is the union of convex shapes. BSP-Net returns a simple CSG object that can be represented by meshes with fewer polygons. It can reproduce sharp edges, which are not common in neural implicit models. BSP-Net also provides good segmentation results. As the network is a continuous function, there is a natural correspondence between the convex parts of the objects obtained when we consider near input vectors. The R-planes figures presents an example. As you can see, each R-plane produces an object which is given by a collection of colored convex shapes. Observe that there is a natural correspondence between the convex parts of each R-plane. ConvexNet is very similar to the BSP-Net, since it also represents the object as a union of convex shapes. However, it focuses more on representing smooth convexes. The results look like an object made of modeling clay, which you can see in the figures. Again, the CSG tree is fixed in the ConvexNet representation. However, this network is capable of representing smooth convexes. On the other hand, BSP-Net can learn a part of the tree and can represent sharp details. I think extending these neural networks to encode more general CSG trees is a very interesting problem. Therefore, other primitives like spheres and cylinders could be used in the modeling. Also, other operations like difference would help in modeling more complex objects. Thank you.
Hello, my name is Alison, and I'm going to present this part of our tutorial on neural networks for implicit representations of 3D scenes. I'm going to talk about the convolutional occupancy networks, a work of Peng and collaborators that was published in the ECCV last year. So the problem is how to scale deep 3D implicit representations to more complicated or large-scale scenes. And here on the right, we have an illustration of a desired result, as we are seeing a shape reconstruction using a point cloud from this dataset Matterport 3D. And we will see how this work achieves that. The research on neural implicit representations is advancing very fast. So we had the first generation of models with works like occupancy networks and deep signed distance functions that use a neural network to represent an implicit function based on global features of our input. And now we have a second generation of models with works like BSP-Net and ConvexNet that were already presented. And this one, Convolutional Occupancy Networks, which tries to make implicit 3D representations more expressive by better representing local features. So implicit representations have many advantages as they are continuous functions and therefore can be used to represent models in arbitrary resolutions, and also have a low memory footprint. So if you encode an implicit function in a neural network, all you have to store are the weights of the network. The first generation of models showed us that we can represent single objects and simple geometries using a neural network. But now the goal is to scale this kind of representation to complex scenes with multiple objects. However, at this time, we are still concerned only on shape reconstruction. So this work doesn't address texture or appearance representation, but as I said, this area is evolving very fast, and we will see some works that deal with this problem later on this tutorial. So the work starts with a hypothesis that the key limiting factor of most simplicity models is their fully connected network architecture. And they say that because it's an architecture that can't incorporate inductive biases such as translation equivariance, and as we were talking, it can't integrate local information, so it's a global representation based on our input. Here we can see a comparison between occupancy networks, a model of first generation, and convolutional occupancy networks, this work from second generation. On the left we have a noisy point cloud, which is the input to both algorithms. In the middle we have the reconstruction from occupancy networks, and we can see that it is organized moved and some objects are aggregated with each other. And here on the right we have the reconstruction from convolutional occupancy network, which looks much better. The key idea here is to look to the successful application of convolutional neural networks to images and try to use this kind of operations, the convolutions, to obtain translation equivariance on 3D. So if you have a scene and you want to reconstruct a scene with multiple chairs, for example, you'd like your model to learn how to reconstruct the shape of a chair anywhere in that scene. And more than that, if you learn how to reconstruct a single chair and you have multiple chairs that are similar to this first one, you'd like your model to use this acquired knowledge to make the reconstruction easier and maybe faster. So we'd like also to exploit the self-similarity of 3D structures in the scene. And they build upon occupancy networks in terms of the implicit function choice, but they propose a new kind of computation of features by combining convolutional encoders with implicit occupancy decoders. Convolutional occupancy networks isn't the first work to publish about the benefits of combining convolutions and implicit representations. As related works, we can cite PIFO, pixel-aligned implicit functions for high-resolution clothed human digitization, and also the ISN, which means Deep Implicit Surface Network for high-quality single-view 3D reconstruction. However, both PIFO and the ISN perform convolutions in the 2D image domain, while the current work proposes to aggregate features in physical 3D space, exploiting both 2D and 3D convolutions. So in convolutional occupancy networks, we have a word-centric representation that is independent of the camera viewpoint, and it aims to make implicit 3D reconstruction at scene level. So how does it work? We start by processing our input, represented here by X, with a task-specific neural network. So in the paper they used a one-layer 3D convolutional neural network for voxelized inputs, and a shallow point net with local pooling for point clouds. And now that you have your input in a space of features, we will build another feature representation that encapsulates neighborhood information. So we can construct a planar or a volumetric feature representation by applying one of these encoders. So the plane encoder will make an orthographic projection onto a canonical plane or multiple planes. So we could use this ground plane here to project our features, or we could use like 3 planes using these canonical planes in this space. And after this projection, we can aggregate the features into pixels by using average pooling. This way, we will get planar features with dimensionality height times width times the dimension of your features, and this for each plane that you choose. Instead of a plane encoder, we could use a volumetric encoder. In this case, we don't need to project the features in any plane. We just make an average pooling by aggregating the features into voxels. And of course, this choice is more constrained in terms of resolution, as we need more memory for voxels. And now, our volumetric feature size takes into account the subdivisions in another dimension. After this first encoder step, we will have a feature representation of local parts of our input, and we will process these features with a convolutional decoder using a U-Net architecture. So this allows aggregation of local and global information. So for a single plane encoder, we use a 2D U-Net. For a multiplane, we use a 2D U-Net for each plane, and for a volumetric encoder, we use a 3D U-Net. Notice that until now, we were only processing our input. We were building a feature representation for our input that aggregates both local and global information. But we want to make predictions of occupancy for arbitrary points in the space. And now that we have this representation, we can take an arbitrary point P of the three-dimensional space and compute a feature vector for this point, given our input X. So if we have a single plane, we project this point P on this plane and compute the feature vector using bilinear interpolation. If we have 3 planes, we can do the same procedure for each plane, and then we can sum the features of all 3 planes. And if we have a volumetric representation, we can do trilinear interpolation to compute the feature vector of this arbitrary point P given our input X. As you can see, we are just interpolating nearby features. So you could question if the interpolation strategy used in the convolutional decoder has any impact on the final result. And the authors compare the nearest neighbor and the bilinear interpolation methods for the multiplane version of the model. And in the paper, they present a table that shows that the bilinear interpolation gives better results in this case. Notice that in the original occupancy networks, we take this point P in the 3D space, and we take the global features of our input to make a prediction. And now in the convolutional occupancy networks, we pre-process our input X to get a feature volume or feature plane. And for an arbitrary point P in the 3D space, we will compute a feature vector for this point P given this feature volume or plane of our input by interpolating nearby features. And now we can use this feature vector psi of P and X to predict the occupancy of the point P using a fully connected network. So we have a model that takes the P and psi of P and X and outputs a value between 0 and 1. For the experiments in the paper, they used an architecture of 5 ResNet blocks and a hidden feature dimension of 32. During the training, we can generate the square point P by uniform sampling inside the volume of interest. And we can use the binary cross entropy loss between the predicted occupancy value and the true occupancy value to optimize the network weights. And for the inference, they applied an algorithm to extract a mesh and visualize it. But as we have the implicit function encoded in the neural network, we can use other approaches. For instance, a technique based on ray tracing. And now we can see some results. So here we have an object level reconstruction. On the left, we have the point cloud as input. On the right, we have the ground truth mesh. These models are from the ShapeNet dataset. And here we can see 3 different approaches using convolutional occupancy networks. So with a single plane encoder, with 3 planes encoder, and with a volumetric encoder. And here we have the original occupancy network, and this point conv is actually the result of applying the PointNet++ to generate features from this point cloud, and then using these features without convolution to make a prediction of the occupancy. So by looking at this image, we can see that fine details are much better here when we look at this object on the top. Although this reconstruction with the volumetric encoder failed to reproduce the corrected topology of the chair. So the holes they are presented here with the multiplane approach, but they are not present here with the volumetric encoder. Here we have the voxel super resolution experiment, and the goal is to reproduce fine details that are not present here in the voxelized input. And as we can see, the convolutional occupancy network using the volumetric encoder gives the right topology and a good geometry approximation. Here we have an experiment on a synthetic endorsing dataset created by the authors, using multiple objects from the ShapeNet dataset, like chair, sofa, cabinet, table, and so on. Each scene consists of a ground plane with a random width-length ratio, multiple objects with random rotation and scale, and also randomly sampled walls. As this image was too big, first we see here the results on the baseline models, which are too smooth as we expected. And now we can see the results of the convolutional occupancy networks, which are much better. But we can still see some artifacts of reconstruction, like here, or the wrong topology here. So this experiment shows an interesting result as the authors tested a hypothesis that plane-based and volumetric features are complementary. It seems that high-resolution canonical plane features can capture fine details but are prone to noise, while low-resolution volumetric features are more robust to noise but produce smoother surfaces. So they combined these features to check if the result would improve, and in fact, it's better to use them combined than isolated. This line combines plane features and volumetric features. However, as we see in the table, the best results in these settings are achieved when increasing the resolution of the volumetric features to 64 cube. Another interesting experiment is the generalization. So they trained some models using the chair category of the ChipNet and tried to reconstruct a table. And as we can see, once again, the convolutional occupancy networks gives a better result, although we can see some artifacts here and here. One of the most ambitious experiments was the reconstruction of large scenes, such as the models on the Matterport 3D. And to do that, they had to break the input into batches with overlapping parts and adapt their model to a fully convolutional structure. This way, the model shouldn't depend on a global coordinate system, but only on local relative coordinates. And it gives a good approximation, but if you pay attention for a minute, you can see that many fine details were lost. So by looking at this wall and this part, you will get it, and also this wall and this one. But it's still an impressive result, as the geometry and point distribution of the Matterport 3D are very different from the synthetic indoor scene dataset that was used to train the model. So this shows that the method can generalize to unseen classes, novel room layouts, and also different sensor characteristics. And this last result is a point-based reconstruction using real-world data of the ScanNet dataset. So first we look at the qualitative result, where we can see that no model is perfect, but it seems that the model with volumetric features performs better. And on this table, we have a quantitative result that confirms this impression. So it really seems that the volumetric features are more robust to noise and perform better in real-world scenarios. To finish this part, let's go to the conclusions. So first, it's possible to combine the expressiveness of a convolutional neural network with implicit representations. And we saw that shape reconstruction can benefit from translation equivariance. It's important to notice that this method is only translation equivariant with respect to translations that are multiples of the defined voxel size, and in particular, it's not rotation invariant. We just saw that by using volumetric features, we can get better results in real-world scenarios, but we have a situation where our resolution is constrained due to memory restrictions. And it's interesting to know that you can use a fully convolutional model to reconstruct large scenes using a slide window. I appreciate your attention. Thank you for watching.
Thanks the authors for the presentations, and now we have time for questions. I looked at the commentary part of the YouTube, and I didn't find up to this moment any question, but if anyone has a question, please place the question in the commentary part, the comment part. I have questions. In fact, I have several questions for each of the presentations. So I will start with the question. Considering the first work I don't know if I'm correct. I don't remember exactly the title of the first work, but I believe it's Occupancy Networks. I'd like to ask the authors how the conditions are used in this method. I know the methodology is somewhat intricate, but if you could talk a little bit more about the conditions in the formulation, it would be interesting if, so we could get other insights about how this method works. Please, the authors.
Okay, so a little bit about that. Actually, the conditioning is based on that. There's one specific part of the network that just deals with that. Usually, you have an auxiliary network that generates a code based on your conditioning. For example, a point cloud or an image or a volume. So you have a specific cloud that generates, and that latent code space is used in conjunction with on the 3D points that are on your space for inference. So it's just that. You have a code that drives the process.
So in a certain way, this is a little bit similar to the latent vector and the latent vector in the DeepSDF and the shape code in the ConvexNet.
Yeah, several of those works deal more or less on the same way with this conditioning part.
Okay.
Usually,
those are specializations of this conditioning in the occupancy network. They are particular cases, I believe.
Yeah.
Okay. Thanks. I have other questions.
Anselmo, deixa eu só complement the answer of Vinicius. I think it would be useful to separate the problem in two parts. And I understand that you were talking about the issue between learning one shape and learning a family of shapes.
Yes.
And as both Vinicius and other presenters stressed, so these are two different problems that are sort of complementary, right? Learning one shape is like a regression problem, right? And learning family of shapes is more like a kind of learning a probability distribution, a condition to some inputs, so another techniques to create this probability distribution for a class of shapes, right? And what I think is beautiful about this area, if you notice, is that the techniques they use are very different from each paper, although the mathematical underpinnings are the same, and they sort of like exploit different characteristics of the implicit representation. So, just to summarize, in the first generation models, what they try to learn is an indicator function. So the implicit representation is a function that gives 1 for points inside the shape and -1 for points outside the shape, or 0 for points outside the shape. And in the second generation models, actually is a sign and distance function. It's a function that is 0 at the boundary of the shape and positive outside and negative inside, for example, right?
Okay.
And we sort of like schedule the presentations in order of complexity of both these techniques. So if you consider just the regression problem, the occupancy network actually does classification. Basically, it's a traditional method. So given a point, it classifies that point in relation to the shape. It gives like a 0 if it's outside, 1 if it's inside, right? And this is very traditional for many problems in learning, right? And then they simply apply this using a fully connected network with the trick that they use this skip connection to stabilize the model, because they want not just to do that, but also to learn class of shapes. And that enters the second part, that there are different methods to learn class of shapes. One is like to condition that, right? And so the first two methods in the first generation models, they use different techniques. The occupancy networks use the conditioning direct using conditional batch normalization. So the idea is you have this basic model, and then you condition to the code that is related to the mean invariance of that input, and use that as a code that is, is augmented in the network, right? And when you have that, you can generate that code from some data. That could be an image of the object or other data that comes for the object that you want to extract from that representation, right? And they use a technique that is used in generative models, in adversarial generative models, because if you notice, Vinicius mentioned the Kullback-Leibniz metric that tries to kind of, is using GANs, for instance, to kind of compare two probability distributions, right? And that is what is optimized. So in the case of the second model that does that, is the second generation model, they use is the DeepSDF, is actually trying to learn a global function that is a sign distance function, right? And then the way they try to learn this class of shapes is using encoder-decoder architecture. But the authors notice that you don't need the encoder, just need the autodecoder. So basically, given the code of the shape, you augmented the input not just with the coordinates, but the code of that shape, and you learn that autodecoder. And there are some underpinnings on that, because you have to optimize so that you have that code for each shape, and then once you have it, then you can recover it from the class of distributions. So I guess I want to give an overview of your question, relating this to all the other papers.
Okay. So you believe there are two classes of problems. One question that I would like to ask is if we could, if the authors, in fact, could somehow propose an overall framework for grouping these papers. If you could present a overall mathematical framework for describing these two classes of problems and classifying each of these papers into these two classes. And if it would be possible to generalize these methods using a general mathematical framework. Do you
Well,
believe that
actually, we
this
we
could be
tried to
possible?
do that on the survey paper, although we didn't present here this yet, and we are not going to present at all because wouldn't be enough time to add this to the presentation. But if you and the SIGGRAPI attendees read the survey paper, actually the survey paper, the first part is actually this, general model that classifies the recent techniques and discusses how they relate to each other. Basically, we believe that there are, four generations of models that evolved very rapidly in the recent years. It started in 19 and coming to the time we presented this, works, 2020 at beginning of 2021, right? So we had like the first generation models that, basically are global models. Then you have like the second generation models that are local models. We have presented both, 2 or 3 papers from each category. And in the second part of the course, we have the third generation models and the fourth generation models. So the third generation models, they learn actually a Euclidean sign distance function. That's a true distance function. It's not just a signed function continuous. It's like the Euclidean distance of any point to the shape. And this is an important property that can be exploited. You will see this in the second part. And finally, the fourth generation models, it actually became an explosion in the area. It's about not just learning shape, but learning the radiance field. And so you learn the shape and the attributes in a volumetric way, in implicit form. And this is like a very active area of research. And the SIGGRAPI this year, there was a course, tutorial course, that's a full day course, 4 hours of presentation, showing the most recent results, some results that are beyond what we presented here because they were produced from the end of 2020 to the middle of 2021. And they actually showed some results that had not been published yet, right? So this area is very active, and I encourage all the SIBGRAPI attendees that are interested in that to pursue, this kind of research.
Okay. Okay. Thanks for your answers and your discussion. I had other questions, but I believe it would be better to postpone it to the final part of the presentation. So now we have the coffee break. We'll stop for 15 minutes and later we return with the second part of this tutorial.
Thank you, Anselmo.
Thank you.
Thanks to the audience. Hope to see you in the next section.
Okay, now we return to the second part of the tutorial. And let's wait for the authors to present the second part.
Hello, I am Luis Velho, and I'm going to present the Siren network. Here we can pay attention to two aspects. The first aspect is the implicit neural representation, and the second aspect is the periodic activation function. These are the two ingredients that makes the Siren a special network. Siren is the acronym for sinusoidal representation networks. The main difference between a regular fully connected multilayer perception and the Siren is that the activation function, the nonlinearity, is a sine function. This has several important consequences. The first is that the network, because of having as the nonlinearity periodic function, this gives the network properties of translation invariant. The second characteristic is that the sine function is a continuous and infinitively differentiable function. In particular, these two characteristics have a very profound relation with Fourier theory. Recent research in machine learning discovered that the implicit signal representation with fully connected multilayer perception networks favors lower frequencies. On the other hand, this same theoretical results shows that if we do spectral projection with the inputs to the network, this allows the multilayer perception to represent higher frequency functions. And this is typically done using like Fourier feature mapping, where we project on the Fourier basis itself, or in the case of the Siren, we project in the sine basis. And so this is the one of the powers of the Siren, and compare it to other networks, regular ReLU MLP to solve the implicit representation problem. It really gives another level of quality, because as we mentioned, it can represent higher frequencies with the details of the signal and formulate the different problems related to signal representations as a continuous function with all the derivatives that can be used in the solution to create different applications with the signal reconstruction. And as we can see here, regular ReLU MLP cannot reconstruct faithfully an image. So it gives blurry results and cannot reproduce the details of the image. In the case of shape reconstruction by implicit function, the result is very noisy and cannot capture all the details of the geometry. And for both the audio and the differential equation, the ReLU MLP cannot even give a meaningful solution. In contrast, the Siren shines in all these examples. So it's important to notice that depending on the domain and depending on the application, we are going to exploit the continuity and differentiability of the Siren network to solve a problem that gives some constraints when we reconstruct the implicit function. Here, we are interested in shape modeling. We are interested in representing implicit shapes to implicit function. And for that, the formulation is a conal equation. So we want a sine distance function from a surface. And the surface is a level set that this sine distance function. In the continuation of the presentation, we are going to focus on using the Siren to represent implicit shapes using the conal equation. And in that respect, we formulate the problem as follows. We have a function f of x is the sine distance from a surface. And what we give to the Siren is the coordinate x and the value of the sine distance function in some points of the domains. And we formulate the constraint as a differentiable equation that involves the conal constraint. So the conal constraint says that the gradient of the function is equal to 1 everywhere. So here would be the loss function of the network, where we break the problem in 3 constraints. The first constraint, as I mentioned, is to be a true sine distance function given by the conal equation, and means that the gradient of the function has to be equals 1 everywhere. And then we want to fit the surface. So we are giving input points at position x that are on the surface, this domain omega 0. So to minimize this is going to favor the solution with phi of x is going to be equal 0. And also we want to align the gradient of the function at those points with the normal of the surface. So we are giving not only the value of the function, but the normal of the surface at that point. If you minimize this, it's going to give a gradient that aligns with the normal of the function. And so this makes possible for us to represent in a very good way the geometry of the surface. And this third term takes account of the other points that are not only on the surface, but are off the surface. So this is a domain that is the complement of the point set, the 0 level set, in the rest of the three-dimensional domain. And so this term forces the values of points that are not on the surface to have a high value. And because the gradient should be 1, these points are going to approximate the true distance function. And so this is the way that are formulated the implicit function reconstruction using a sine distance using the Siren. So now we are going to discuss machine learning framework using the Siren. And we are going to divide this in 4 parts. The first part, we are going to discuss the mathematical model behind the Siren network to deal with this problem. And we are going to see how the network gives implicit neural representations to be solved using machine learning. And then we are going to discuss the architecture of the Siren, how this representation is encoded into a multi-layer perception with sign activations. And then we are going to discuss 2 important aspects. That first is the initialization of the network and how this relates to frequency distribution. And then we are going to see how the network is trained based on the input data. So the samples of the our surface to be reconstructed. Okay, so the implicit neural representation, basically, we have this function f that we want to be equal 0. So f is going to involve the coordinates x and the function phi and the derivatives, higher order derivatives of this function. So the gradient and the other higher order derivatives. And is a function that is going to be given by some samples at some points with the values. But we also are going to encode properties of the function as different constraints. So we have m constraints that involves the attributes of the function, the input data, and also the function itself and all derivatives of higher orders. So we have like m constraints. Depending on the problem, these constraints are going to be different. And as we saw in the case of the equal equation, here we have like 3 constraints. One for the equal constraint, other to fit the surface, another to give the distance function. So, and the specification of a particular geometry, a particular surface, is given by the data, the input coordinate xi, and the function value ai. And we have a loss function, as we saw before, that includes, in the case of implicit function, 3 constraints. And the network aims to find a function phi given by the network, the parameters of the network, that are going to satisfy all the constraints, that says making the constraints equals to 0, right? So this is the implicit neural representation. And the neural representation is encoded by neural network with fully connected multilayer perception architecture. So basically, the parameters of this network that's representing the function are the weights of the multilayer perception and the biases of the multilayer perception. So typically, the network is a concatenation of different layers. So we have a composition of these layers, phi I, that have as input features xi. As we mentioned, the parameters of the network are the weights from this weight matrix for each fully connected pair of layers, and the bias associated with each layer. And after this affine transform, you take the input, multiply by the matrix, and add the biases. We apply the sign non-linearity. And this network has a width that's the number of layers, and each layer has some number of neurons. So typically, a Siren network has 3 to 5 layers, each with 256 to 1,024 units or neurons. Now it's important to discuss important theoretical aspects of the Siren network that makes it to learn fast and in a stable way, is the initialization. Or the initialization, we can imagine two parts of the network. The first layer that, as we discussed before, does this spectral mapping that projects the input coordinates to the sign basis. And then the hidden layers, they are initialized in a way that they give a kind of very stable training, because in the paper, the authors prove a theorem that says that if you distribute the weights in the based on uniform distribution that's from square root of 6 divided by the number of the input signals in each layer to 6 divided by the number of input of the layer. This is going to guarantee, independent of the layer in this hidden layer sequence, the input of each layer is going to be distributed as a Gaussian function, and the output is going to be distributed as the arc-signed. And so this is going to give like a normalized and very stable situation for training. And now, to finalize, we have to discuss how the training is done. So to train, what is done is that we divided the data points from points that are on the surface and points that are outside the surface. And for the points on the surface, we compute the normal of the surface and assume that the value is 0. And for the points that are off the surface, is going to give only the coordinate. And then the network is going to figure out the value based on the solution of the equation. And these two kinds of samples for the data, they are going to be given to the network using mini batches. And so for each mini batch, like 50% of the points are on the surface and 50% of the points are outside the surface. And we did some tests and evaluation of the Siren, analyzing its convergence, analyzing the capability of representing fine details of the geometry, and figure out the network capacity to represent different shapes of different complexity. So here is an example of the tie statue. The tie statue is a data from the Stanford 3D scanning repository, and the input model has 10 million points, and the network in this case had the following configuration. Is a 5-layer network with 206 unities. And here you can see that the network is able to reconstruct very faithfully the fine details of this scanned statue. Here we see a detail of the elephants of the statue with all the details in the different parts of the geometry. And now we can show the experiment with the room, a scanned room, and has the same number of points, 10 million points, and the same number of layers of the previous example of the tie statue. But here, because of the geometry is much more complex, we need more capacity. So we have like 1,024 unities. And if you see the solution here, we see that the solution is not perfect. And that's because we stopped the conversion after 5,000 iterations. And so we can see that with only 5,000 iterations, we have a very good solution. And this shows how the network trains fast and converges quickly to a good solution, and then it can continue until you get better results. This was the presentation, and I thank you to be listening.
Hello everyone, I am Luis Sherman. I'm a postdoc researcher at INPA and a research assistant at PUC-Rio. In a previous video, Professor Luis Velho presented the Siren neural network. Here, in this section, we will talk about the implicit geometric regularization for learning shapes, an alternative model to the task of reconstruction 3D shapes proposed by Drop et al. And presented at ACML last year. One way to represent 3D shapes is implicitly, as a zero set value of some function. However, if you think about simple shapes, just like spheres, this representation is well known. However, this is not the same for complex shapes. For example, here, a human shape. One way to represent complex objects implicitly is using a Siren distance function. This representation models a surface defined by the boundary omega. The distance to this boundary defines the implicit function, where additional information describes if a point is in the interior, exterior, or at the surface of the object. Several papers propose to use deep neural networks to approximate an SDF. However, here, the main goal of this work is to generate to learn complex shapes directly from raw points. The authors utilized the connection between SDF and the diagonal partial differential equation. So let me first explain this diagonal PDE. This is a nonlinear PDE, and the nonlinear part comes from the fact that it requires the norm of the gradient to be equal 1 everywhere. It also has a boundary conditions that requires an unknown function to be 0 in some nice boundary conditions, namely on some manifold, just like here this example, the omega boundary. If the boundary conditions are nice, the solution to this equation is unique, and it is the SDF. However, let us here break the rules. We want our function to be 0 at this bunch of points here, which is a non-manifold, and we want to compute the SDF. As I said before, if we want a well-behaved boundary, a manifold, a well-behaved boundary, the unique economic solution is an SDF to the surface. However, here we have two plausible solutions for this condition, or this boundary condition. Okay. So in this example, we may have multiple SDF solutions. Think about here. We have just this line and this crazy curve that traces that kind of traces these points. If you compute an SDF to this curve, we have achieved the solution to the PDE, and the same here. So how we can solve this problem? The authors suggested the following loss function. The first term forces the network to vanish on the surface points, or if you prefer, to be zero on the points. And the other components solve the Econol equation. Optimizing this loss, the deviation from the Econol condition would be minimum across the domain. Optimizing this loss surprisingly favors the neural network to converge to a simple, the most simple SDF solution among all possibilities of the Econol solutions. This is the same for this line, or the circle, or this crazy form here. So, considering this, okay, the intuition here is that the neural network has a geometrical version of the well-known implicit regularization phenomenon in neural network optimization. And the authors call this the implicit geometric regularization. So, when we have also additional information, for example, the normals to some surface, or this example here, the oriented normals at the points, we can naturally improve our loss function just by adding a normal reconstruction term. Okay. The main architecture of this network proposed by the authors is a simple feed-forward neural network. Each layer here is a fully connected linear layer. We have a just where the input data is concatenated to the previous layer output. And of course, the output of this neural network is the calculated SDF. Okay, but now just like in Siren neural, in the Siren neural networks to reconstruct 3D shapes, we need our loss function to be differentiable. So the authors here consider a smooth approximation of HELU, which is differentiable in all in the domain. So this is called the soft plus activation. So let's consider this example here. IGR can force a neural network to produce high-quality surface reconstructions with high levels of detail in 3D. And let us consider the evaluation following a benchmark proposed by Berger et al. With this dataset contains input point clouds and the normals for 5 different 3D shapes. The authors compare their technique with the baseline DGP, which is a chart-based technique for shape reconstruction. The table here shows the chamfer and the Haseldorff distance to the ground truth. As you can see, IGR outperforms this paper, which is the previously state-of-the-art. Also, with the false dataset for human shapes, the IGR can achieve state-of-the-art reconstructions considering implicit representations with neural networks. So here we have 2 scans from the false. A 3D scan from a human shapes, for example, for a man and for a woman. Okay, so with these 2 scans from the false, the author sampled it with 200,000 points, something like that. And for each point, they take the normals and produce two samples, one for a regression task, okay, and the same data to produce an IGR reconstruction. So here we have these two results using the same neural network with the same parameters, the same architecture, except by the loss function and the activation function. So as you can see here, the IGR can produce reconstructions with much more details. And also, when we compare IGR and Siren, we can see that the IGR can outperform this technique in some cases for noisy datasets. In this test, we use the dataset from the ShapeNet and the surface reconstruction benchmark proposed by Burger. So the intuition here, consider why the intuition here about this behavior is considering these spheral components here. So the Siren do not have an SDF outside the points on the surface. The IGR performs an SDF approximation for the points out of the surface. Also doing a theoretical analysis about the IGR, the authors show the intuition behind the property of linear plane reproduction. If the points span a d-1 hyperplane in RD, the gradient descent will converge to the correct SDF, forced by the IGR loss function. So let us consider this following 2D visualization, the 2D landscape of this loss behavior. Let us assume that the input points span this y-axis here. So here we have 5 critical points. 0 is a maximum, 2 saddle points, minus alpha E2 and alpha E2, and 2 minimum, minus E1 and E1. Okay, the gradient descent will evade the saddle points and converge to an SDF solution for any starting point, orthogonal to the y-axis. So the probability of conversion is 1. For the general case in RD, we have at least 3 critical points, including the maximum and 2 SDF solutions. Okay? The rest of the critical points have negative eigenvalues, so they are maximal or saddle points. And considering the proof provided by Lee et al., the gradient descent evades saddle points with a probability 1. So this concludes the proof for the IGR plus. The authors also consider the noisy case where the data is sampled from the hyperplane with additional bounded noise. Also, in this case, it's possible to find a specific lambda that guaranteed the conversion to a good SDF solution. Okay, so far we have talked about the representation of a single shape, but another exciting task is to learn a latent space of multiple shapes. So to do that, the authors use an autodecoder architecture suggested by Park et al. Okay, a latent vector here, Z, is concatenated to every shape in the dataset. Then, both neural network and the latent vector are optimized in training to minimize the IGR loss. In the inference, the neural networks were freezed, so the neural network weights are fixed, and the latent code is optimized. The architecture is very similar to the previous one, except due to the fact that we concatenated latent vectors. In the middle layer, the size of this vector affects the number of the neurons used. As we can see here, using IGR, it's possible to interpolate the latent vectors and navigate through the latent space. For example, here we have this gray models, which is a result of the interpolation of this its neighbors. So what they do here is they took some latent shape, for example here A and B, and they do the average and reconstruct the model. I think here that the point here is, for example, if we look to the quality of this interpolation, okay, considering its neighbors, so we look at the morph of these figures, and we can see that the details are very plausible. Okay, so it really looks like something between its neighbors here. Implicit geometric regularization is an important approach for solving the problem of shape reconstruction. Implicit neural representations have been a very active research field, especially since the last year. So here, let me suggest some interesting future directions. Maybe we can improve the quality of reconstruction using sinusoidal activation functions, combining the power of Siren and IGR, or are maybe combining IGR with implicit differentiable handling to learn both shape and material. Why not? So, if you have any questions, I would be happy to answer in the QA section. For more details, please visit the project man page. Thanks for watching.
Hello, I'll be explaining two recent methods that do differentiable rendering using this idea of deep implicits that we have been talking about in this tutorial. So, to contextualize the problem, let's remind ourselves about what differentiable rendering means. So first, the regular rendering, we have scene parameters like camera pose, geometry, materials, etc. And we want to generate a corresponding image from these parameters, and that's our traditional rendering process. And then differentiable rendering, what we want to do is that we are interested in having some feedback from this process. So either from the actual image, the resulting image, or from the process. And that allows us to learn about the scene parameters and about the process itself. So this is very useful for many applications, inverse graphics, for example. And as we're going to see in the deep implicits context, we're going to be interested in reconstruction of geometry and also in the appearance parameters. Okay. So the first method I want to talk about is the differential volumetric rendering. It's from this group from Germany, right? They were the same. They also worked with the occupancy networks that we have discussed, and they are interested in the problem of self-driving cars and the idea of the AI being driving a car, and then they see a 2D scene, right? A 2D representation of the real case, for example, cars, and they want to reconstruct or to infer 3D information about the scene, correct? And then that's the whole idea for them to try to work with these deep implicits. And so they got to the question of, can you do implicit 3D representations without 3D supervision? Why this question? If we remember the methods that we've been seeing, we do need 3D supervision to train our methods, and that's not a very available thing. You know, like you want to train in a real scenario, and you don't have 3D supervision in general. You don't have the models about the real life. You just have photos, for example. So you want to learn this 3D information without the 3D supervision, only with 2D information. So that's what is the question, is that's what they try to solve. So what do they got? They actually are able to do even single view 3D reconstruction. So from a single image, they are able to reconstruct a 3D model that would represent such image. We're going to talk about how exactly they do that, and they also extend the problem to multi-view reconstruction and get even better quality. So what is their architecture and idea of their problem? So the idea is that we have an occupancy network or a deep implicit, right? That would represent the geometry of the problem. Okay, so with this occupancy network, you have your actual implicit surface, and they use a condition. So if you want to do single view reconstruction, the idea is having another network here that creates this encoding, right? And then feeds into the occupancy network and also to a texture network. So we also are able to create this texture map, this implicit texture map, right? So these are our functions. So this is an occupancy network. This is a texture prediction function, which will predict the color in the image. So the pipeline is, you have your sample pixel, your coordinate. You use your occupancy network to find a point in the surface that you want to render, and you have the option also of having a supervision with a depth map, but it's not necessary. They do test with both cases, and then you can render the actual color and have the final image, and this encoding will reinforce the image that you want to use. Why the encoding? Because in the single view case, what they will do is that they will train this network in several different images and objects. So maybe like a class of cars, or maybe several classes together, like planes, regular objects, chairs, tables, stuff like this. And then they will expect that with a single view, you would be able to learn 3D geometry and coloring of the object. Okay, now how this process works. Okay, so let's go first through the forward pass, so how the rendering occurs. Okay, so the rendering is you have an array, right, that goes through your camera position into the image, and you want to know what is the color in this pixel U here. And then what we write here is that what we are interested in is in finding this point that intersects with the surface, right? So this is our surface from the occupancy network. This is like a threshold. So you want to find this P hat, and then we're going to use the texture map on this P hat, and you will have the correspondent color for this point. Okay, so how you do that, you in practice what they do is that they throw this ray, and then they sample like n points, some quantity of points, until they find a difference on the if it's smaller or bigger than or larger than tau here, then your threshold. Then after you find this first point, you do like a second method to root finding, right? And then you go up until you find your root, your point of interest here. So it's like you're trying to do a root finding numerical algorithm to find this equation. Finding P hat, we can compute this guy, and then you have your color, and then you render your image. Okay, what about the differentiable rendering part, right? Like how do we compute the gradients? Of a very simple loss is just the displacement from the pixels itself, from the color of the pixels. So this I hat is your predicted image on the pixel U, and then you just do like an L1 distance, right, from these two, and so you just want to know how close each pixel is. And then we want to differentiate this, and how we're going to do this. So first we can just like break this regular like chain rule and stuff, and we're going to have so you want to differentiate with respect to the parameters, so we can break into with respect with the I hat U, which we know, right? And we want to know this guy. So this is already known, it's from the function itself, and then now we're going to rewrite this with respect with the texture map, and then texture map, so IU is the texture map applied in P hat. To differentiate this, you have to differentiate in your first coordinate with this theta itself, and then you have to differentiate in P hat, but P hat is also a function of theta, so that's why you get this form. Now these two guys you can get from the network itself. The one that remains to be seen how to compute, it is less trivial, is how do you compute the derivative with respect to derivative of the intersection point with respect to theta, with the parameters. So their idea is this depth gradients concept. So what they do is that they write the point P hat as a function on this ray, right? So you have this ray function, the cast array from the camera position to the surface point, and you have this W, which is the distance until the image, and some D, which will be kind of the distance between the surface point to the camera position, R0. Then, so what you do is that, so we can find d hat, right? We can define d hat as a point such that p hat is equal to r d hat, right? So in this function, so we find the d with respect to this p hat, and what they do is that they differentiate this function, this equation here, both sides, and then you will have something in function of d hat, okay? And then having something in function of d hat, right, you have your r0 disappears, and you have d hat d hat d theta times w. And then what you want to do is compute the derivative of d hat with respect to the parameters. To do this, their idea is to use like an implicit differentiation, right? So you have f theta on p hat that is equal to tau, right? Because p hat is on the surface, so f theta p hat must be equal to tau, or like near tau. Then what you do is you differentiate both sides. So differentiating both sides, you have for f theta p hat, you have something like this, but with f, right? And then what you have remaining is something that depends on d. And then what you can do is like you can reorganize your equation. So the side that you had tau, it became 0, right? So you can pass the summing part to one side, and then you can invert and have this equation for the gradient of the depth. Okay? So it is a function of the derivatives of the network itself, and then that we can compute. Okay. So now we already have the full pipeline to differentiate our new model, and now I present the experiments that they did. So they did 2 experiments, essentially, the single view reconstruction, 3 experiments. Single view reconstruction where the supervision, so the supervision is done with many images, right? Many objects and many images. So a single network is able to do single view reconstruction in many images, actually. So their idea is training supervision in, I think they did 13 classes. And then the idea was they tested doing multi-view on these 13 classes before doing single view, or doing single view for all the training examples. Okay, so they do these 2. And both had good performance. So what they saw is that even if you're training only with single view, you do learn geometry properties about the problem, and which is very interesting. The second problem which they did was using multi-view reconstruction, and then you get a much more rich and with more details, right, about your 3D geometry, and which is very interesting too. So it's the same concept, but with a multi-view instead of a single view approach. Okay, now passing to the second model, gonna go a little bit faster, I think. So implicit differentiable rendering is a bit more recent than the one before, and they try to do this entangling from the geometry and appearance. So they want to do differentiate them, and it is so. The problem is, given some rough camera positions, noisy camera positions, you want to infer the geometry, the appearance, and also correct the camera positions. Okay. So the method uses SDFs, which is similar to the occupancy networks, but you have a distance function, a sign distance function, and your surface is in the 0 level. Okay. So here our theta will be the geometry parameters. Okay, and they also use this regularization that we talked in the tutorial here. The forward pass, so the rendering process, they do also raycast, right? And so our x hat here will be the first intersection as before, but here the raycast, it depends on the tau, which is a camera parameter. So here we're also correcting the camera, learning about the camera, right? It's not totally given. It's given but noisy. So you have a start camera, and then you're going to update the camera position too. So you have your raycast, which depends on tau, and you have x hat, which will depend on the geometry and the camera position, and that's your first intersection. So that's our old p hat, right? And the appearance, so LP here is the actual color on your pixel. So you want to know the color in your pixel here. So what you do is that you have your ray casting, and then so LP is like a light field function that you have the radiance that is incoming x hat. We have information about the normal in the geometry. So the normal here will be a function of the geometry. Okay. We have your direction v. We have the appearance parameters. So m will be our neural network. And we also have this z, which is a global geometry feature. So we want to render considering the whole geometry, right? You have other points that could throw shadows and have effects on your appearance. Differentiable intersections. Okay, so how they do the differentiating part. So that's the pipeline. You know, F is the geometry and M is the appearance. Similar to the other before, but they actually had maybe an even smarter idea. It's kind of a generalization of the depth gradient. So they are able to prove that x hat has this closed form, okay, also using the implicit differentiation idea, okay, and they actually implement this explicitly in their pipeline, okay, so they don't do raycasting anymore. They will do this smart idea of using the f itself in previous points to compute your intersection. And then we have the results. They did the multiview reconstruction, which you have very nice results. So you have both the geometry and the appearance parts. And then what they do finally is that they show that you can actually disentangle them, right? You have two parts, one that cares all about the geometry and one that cares all about the appearance. And they are able to switch. So here you have geometry and appearance, and then you switch the appearance between these two. And then you are also able to have very nice results with this switched geometry and appearance. And they also tested that the normal is necessary for this to happen. For have some generalization of the appearance, you do need the normal. Without the normal, this switching doesn't really work. Okay, so that's what I had to talk, and thank you.
Hello everyone, thanks for coming to my talk. I'm Thales Magalhães, I'm a master student at the SIBGRAPI lab at IMPA. Today we'll be talking about neural radiance fields, so we'll be taking a look at what they are, how they work, and we'll talk a little bit about what makes them special compared to other neural scene representations. We'll also talk a little bit about the current state of the literature at the end of the presentation. That will be very quick. And then I'll refer you to places where you can research more if you're interested. So, first of all, I think it's important to talk a little bit about motivation and where nerves came from. So nerves were created in the context of novel view synthesis. So the original purpose of this architecture and this method is to take a set of images, right, accompanied by camera positions, and to train some sort of scene representation based on these images to be able to render novel camera poses and positions that have never been seen in the dataset. So here, as an example, we have a drum set, and you capture images in this hemisphere around the drum set, and we want some sort of method to render images in between those that we have in the dataset but are not present. So that's the original purpose of this method, this neural radiance field method. And what's important to note here is that we're working with 2D images with no depth information. So all we have in terms of supervision are colors and camera poses. So we'll take a quick look at other sorts of scene representations that might be useful in this context, and we'll talk a little bit about why they're not necessarily the best choice for this particular problem. And we'll start with implicit neural shapes, which you've probably seen in the other talks in this tutorial. But we'll give a quick overview of why they're not necessarily the most appropriate in this case. So an implicit neural shape is when you represent a scene using implicit surfaces, which are functions from R3, so the Euclidean 3D space, to R, so a scalar. And typically this is either an indicator function or a distance field, and the surface is defined by a level set of this function. And as the name implies, we represent this function using some sort of neural network that we train to match the observations that we have. So this is very good in some aspects, right? I mean, it's an inherently geometric representation, so it's very useful if you want to extract geometry from such a representation, because you can basically run a cube marching algorithm on top of your result, and you have a mesh that you can work with other algorithms. But in this context, it's not ideal because it's very hard to optimize from ground truth images, right? So training implicit surfaces usually relies on volumetric data, so either points in 3D space or images with depth attached, or some sort of approximation of the depth. And while you can train these representations directly from images, it's a very difficult task. It's not very straightforward at all. So another limitation is that by itself this representation doesn't approximate the appearance of the scene. So you only get the geometry of the scene. And if you want to encode something like materials or colors, you have to combine the implicit surface representation with something else. But more than that, in that even if you have some sort of material or lighting representation, you can't encode transparencies, because the implicit surface representation is very binary, right? You either have a surface at a point or you don't, and you can't have transparent surfaces, because then you couldn't represent that using this very binary decision that you have to make when you have a surface built on top of a function as a level set. And then we also have voxel-based representations. So in this case, you have a discrete representation of your scene, unlike the implicit surface representation, which is continuous, and it's volumetric. So usually you have a regular 3D grid of samples, and these samples contain both color and transparency information. You can think of this as essentially a stack of images, right? And you render this volume using ray marching techniques. So this is sort of the opposite of implicit surfaces, in that we now have these appearance estimations, right? Because we have colors, we have transparency, and they're very easy to render differentiably, unlike implicit surfaces. But then you lose some of the advantages that you get with implicit surfaces. So now instead of a continuous representation, you have a discrete representations, because you're representing the scene in terms of voxels, which are discrete units. And I think the largest limitation of this method of representing scenes is that it has a very large memory requirement. So you have this dense representation of a scene that is volumetric. So the memory requirements for storing a scene in memory or in disk grows to the order of n cubed. So as your resolution grows, your memory requirements grow much faster, and it's not feasible to use this sort of representation for higher resolutions, because memory becomes a limiting factor. And another limitation is that we don't have any way to encode view-dependent effects. So as you store just a color value per voxel, you can't recreate specularities, for example, that you get in a real-life scenario. So this is where neural radius fields come in. Neural radius fields can be thought of as a sort of compromise between these two approaches, in that it represents the scene volumetrically, but in a continuous way. So your representation of the scene becomes a function from R5 to R4. So you have this function that takes as input a position in space and a direction, and it outputs a color and a density. So you can have, for example, different color for different viewing directions, which allows you to encode specular effects, unlike voxel-based representations. And we, of course, model this function using a neural network. So this is similar to the voxel-based approach in the sense that it represents the scene volumetrically and in a fuzzy way, unlike implicit surfaces. But it's also similar to the implicit surface representation in that it's continuous and it has a very low memory requirement, because you're encoding the scene in the weights of a neural network. So this fuzzy nature can be particularly advantageous for some scenes where you have a lot of detail, and trying to represent the detail in a very binary manner can be a problem. But the downside is that it becomes more complicated to try to extract surfaces from this representation, although it's not impossible, of course. So how do you render such a representation? Well, the approach is very similar to how you would render voxel-based representations, except that you have a continuous function that you're trying to render. So you're, in theory, doing a continuous integral to try to compute the color of a ray that you're casting. So you get this continuous integral where you're accumulating the given a transmittance value that is computed by accumulating the density along the path of the ray. Now in practice, we can't compute this integral analytically, so we use Monte Carlo methods to estimate them. And that becomes a finite sum, of course. And that's very useful in that it's trivially differentiable, because we need that differentiability if we want to train a neural network based on the rendering process. And if we have a rendering process that's not differentiable, then we can't run the backpropagation algorithm to train the network on a particular scene. Now, something that's also important here is that if we try to sample in the most straightforward approach, which would be to sample uniformly, we have this problem where we may lose high frequency detail. If we don't sample densely enough, we might lose some details in the scene. And although we can increase the number of samples to try to capture those details, that number of samples becomes a limiting factor very quick, because each of those samples needs to query the neural network. That can be very slow. So the approach taken in this paper is actually a two-step approach, where in the first step, you do the regular uniform sampling, but then from those samples, you estimate a distribution that you will use to sample again from the same ray, and that becomes a sort of importance sampling approach, where you try to sample from the parts of the ray that have the most contribution to the final color. So then you evaluate these new samples, which hopefully will be near the most important parts of the ray, so near surface boundaries and things like that. And then you compute the approximated integral using those samples and the densities provided. So the architecture of this network is actually rather simple. So it's a feed-forward network with 9 fully connected layers with relay activation. So as you can see here, it's a pretty straightforward network. Besides a couple of skip connections, it's basically just a feed-forward network. So one thing to note is that the density part of the output is computed using only the position. So that makes sure that the density doesn't depend on the viewing direction, but the caller is dependent on the viewing direction, so it uses both parts of the input, both the position and the direction. So training is performed essentially using L2 loss, comparing the color of the rendered image, so the predicted image by the network is compared to the real image, and we compute the difference between the colors of the pixel, and that error is backpropagated through the network until we reach sufficiently good accuracy. Then we can stop the training process. Now, one key insight in this paper is that, as it turns out, the method as described so far doesn't quite work as it's advertised, because if you try to implement this network and this training process as is, you won't be able to match your input images as well as you'd expect, because, as you may notice, you lose a lot of high frequency details, which may be important if you want to render accurate novel views. So as it turns out, this is not a problem that's inherent to this particular domain of trying to represent scenes volumetrically. Actually, you'll find that if you try to use a vanilla feed-forward neural network to learn something as simple as, for example, a 2D image. So imagine that you have a 2D image that you want to train a network to predict. So this network takes as input an XY position, and it should return the color of the image at that position. You'll find that if you try to do that with a standard network, you won't get very far. So this is due to the fact that these sorts of network, they tend to learn lower frequency information much faster than they learn higher frequency information, and they sort of prioritize low frequency information. So at the end of the day, you'll get a network that represents an overall picture of the image you're trying to encode, but you won't get a very accurate result. And the solution here is due to the fact that the input is very low dimensional. So you're trying to train a neural network to predict the colors of an image based only on a 2D input. That's the X and Y position. And the solution essentially involves increasing the number of dimensions of that input. So this technique is called positional encoding, and it essentially performs a basis expansion to augment the number of values that you have on the input, and you encode the coordinates of the input using multiple sinusoid functions. So instead of taking just a single value, for example, the x coordinate and the y coordinate of the image, you actually pass these coordinates through a transformation where you take several sines or cosines with different frequencies for each of these coordinates, and you feed this enlarged vector to the network instead of feeding the bare x and y coordinates. And as it turns out, as simple as this solution may seem, it actually solves this problem of being capable of learning high frequency details. So as you can see here in this example, here we're trying to train two networks to remember these images, except that the network on the left receives just the x and y coordinates to train, and the network on the right receives the coordinates after they go through a positional encoding step. And it's very obvious that the network on the right, first of all, learns much quicker than the network on the left, and also reaches an overall accuracy that's considerably better than the network that doesn't use positional encoding. Now, in terms of nerfs, here we can see two examples of what happens when you don't use positional encoding versus when you do use. So on the left, we have this image of a fern where, even though this network has been trained for several dozen hours, it can't quite capture the high frequency details of the scene. In particular, the leaves, they look rather blurry. Whereas in the image on the right, we're using positional encoding to feed more information as input to the network. And you can see that this makes a huge difference in terms of the accuracy of the result, where the high frequency details of the scene are maintained as expected. Now, let's look at some results of this technique of using volumetric rendering with neural radiance fields. Now here we can see a couple of examples of novel view synthesis. So here we have real world images, right? So we have a few images captured of these objects, the fountain on the left and the plant on the right. And then we train a network to generate these smooth transitions between the different photographs. And you can see that the result is pretty convincing. It looks as if it were filmed in real life. And here are some more results where we do the same thing with real world images. And you can see that the results are pretty convincing. Here we see an illustration of how the network learns to output different colors for different viewing directions. So, for example, we have a visualization of how the network represents a particular part of the water in the scene. Since water is highly specular, so you would expect that from certain viewpoints you'd get different colors, and that's what you get here. So for some viewpoints the color of the water is dark green, and for others it's near white. And here we have a visualization of this effect of different colors for different viewing directions in a real scene, where the camera is kept stable, but the viewing direction changes, and you can see how the color also varies. depending on the specularity of the surface. Here's another example of that. So another surprising result that you get when you train this network to represent scenes is that you also get depth reconstruction almost as a side product, because you're training this network to estimate the density of the scene. So with that, even though you don't have depth information in the input or any volumetric information at all, you actually get this very good estimation of the depth of particular parts of the scene, because that's something that we train in the network when we try to reproduce these 2D images in renderings. And you can see that even small details are captured in these estimations. Now here's something interesting that you can do with these results. You can use these depth estimation to mix traditional 3D primitives, for example, this 3D ball, with a NeRF image. Because you have the depth information, you can actually blend these two representations and mix and match them, which is something that's pretty interesting that you get almost for free. That's not something that you supervise for necessarily. Now, that pretty much covers the original paper on neural radiance fields, but there have been many follow-up papers since then that try to improve on the original design in many aspects, like relighting or editing or training on unconstrained videos. So if you're interested in learning more, I'd highly recommend looking at this GitHub page called Awesome Neural Radiance Fields, where you'll find a curated list of some of the most influential papers in this area. And I definitely highly recommend that you look into it if you're interested in learning more about this subject. So that's it from me. Thank you very much for your attention, and goodbye.
Okay, I really would like to thank the authors for this quite impressive tutorial. I'm very glad to be participating here today in this presentation, and I was really impressed by many of the work that you have shown here today. Especially the last two works are really quite impressive, in my opinion. Uh, I wasn't aware that this kind of methods have advanced so much, and I was really impressed on the nerve and the previous one is sorry, deep implicits for differentiable rendering. I was really impressed by these two last works. The other works are very impressive, are also very impressive, but these two ones were fantastic in my opinion. We have time for some questions. I tried to read the comments here, and I again didn't find any question from the attendees, so I will try to formulate some questions here. In fact, I have lots of questions, but we don't have time to discuss all these issues. I'll try to formulate some more general questions. Concerning the last work, the neural radiance fields, I don't know if I'm wrong or I'm correct, but it seems to me, if I'm wrong, please correct me. It seems to me that the neural network is learning in its weights some sort of planoptic function. Is it correct or wrong? I don't know if I captured the way it works.
Yeah, that's absolutely true.
Okay. I really don't know how it extracts the depth from the planoptic function, but okay, I'll try to read the paper later and discover how this works. Also, I would like to ask the authors regarding the first methods, mainly using implicit representations. How do they What's their opinion? What's your opinion about um, how these methods compare to the classical ones? For example, how this neural network implicit representations compare to the classical power curves, for example? What do you think about this? I don't know if I was clear in my question. I'd like to know what is the opinion of the authors when they compare the classical implicit reconstruction, for example, Poisson equation, with the more modern neural networks methods.
Yeah, I think first it's data driven. So you have the data and you can model based on that data. And depending on the work, some are more based on overfitting for a specific model, and others try to generalize it, and you uh, uh, make the inference for something that was not seen before. So I think this is the most important difference, because it's really data driven, and the network tries to model the specific aspects of the data. It's different for the traditional methods that you have a specific algorithm, and it does not usually learns anything about the data. You just apply the algorithm and it tries to reconstruct.
Okay, okay.
Let me
I think
complement. Go ahead. Right, Chuck.
I would like to add that the neural network you can define a neural network that can represent can approximate very well implicit functions. For example, you can consider the network larger or wider, then you can it allows you to learn all kind of functions, because there is this theorem that you can approximate every function using a neural network. So you can consider this theorem in this setting, and you can have a very well approximate a general implicit function using neural network. I don't know if I.
Okay.
Yeah, let me complement a little bit on what Vinicius and Thiago said. I'm glad that you mentioned, the Power Crust work of Nina Menta. I'll be back to this in the end, but the first thing is that although there are methods that are data driven, they are you have to formulate in closed form. Like, for instance, you can have like a reconstruction form, RBFs, right?
Okay.
And we have done work on that in this graph. And let's say if you want to include like reconstruction from RBF, that's a regression, a problem, but you have the closed form solution with, a kernel basis, right? First, you need, a lot of points, and then if you try to, make this more effective, putting, for instance, the normals, right, higher order information, then you have to again, formulate the problem in closed form. And every time you go through a step like this, it's a lot of work, and you are restricted to that formulation. So as Thiago pointed out, you have much more flexibility with a neural network approach, because you learn, the formulation, and basically amounts to, design a very good loss function and choose the right kind of neural network architecture. So this gives a lot of flexibility. And as Thales pointed out in this last presentation about NERF, not just you, but a lot of people, when they saw that work, got very impressed. And especially because it's so simple, it's a very simple network. There are kind of few tricks that make that work very well. One is that spectral mapping that I mentioned for Siren that they also apply. There's a key technique that everybody uses when they found out that was the trick to get high quality and details, right? But then you can extend that in many different ways, like for instance, separate the geometry from other conditions. For instance, you want to, because the basic nerve learns the planoptic function from a kind of a constant situation, like all the lights are defined, the object position are defined, everything is defined. But if you want a dynamic scene where, let's say, the lights are changing or the objects are moving, then the basic nerve cannot do it. But if you can change the problem a little bit and change the network a little bit, you get that. So this is a lot of follow-up work that I mentioned in the end of the first part that like this SIBGRAPI course this year basically addressed, and that's the power of doing machine learning graphics. It's a new area that everybody's calling AI graphics.
Okay.
Thank you. Just going back to your comment about the power crust, one thing that haven't been tried yet, and because if you think about the work of Luis Henrique at IMPA and Nina Menta, if you have sampling of points in a surface and you compute the distance function, the true distance function is the Diagonal equation, the complement of that is the skeleton, right? And the power crust actually gives you that skeleton. Okay. And that is a very, important information relating the maximum tubular neighborhood of the surface.
Yes.
And you can encode the geometry in a very nice way using that. So theoretically, if you have the Diagonal equation, you could somehow represent the middle X transform, the skeleton of the surface, and then use that for many things, including representing the surface itself.
Yes.
Right? And this, I think, is a promising area of research.
Okay. I'd like to finish by asking you a final question, a more philosophical or general question. Do you believe that all these methods that you have presented here make part of this new area that people have been calling geometric deep learning? Because I've been reading lots of research dealing with non-Euclidean data, and I was thinking if the methods that you have presented today can also be considered geometric deep learning methods.
Yeah, if I'm not wrong, geometric deep learning is actually a way to classify deep learning in such a way that is very near with people who have done with geometry, the math people, the theorems, and it's related with a lot of very interesting works, and they had a geometry classified in a very interesting way that is used by a lot of mathematicians. And so geometric deep learning, if I'm not wrong, is in this direction. So I think it is associated because it's a way to classify everything that is deep learning.
So you believe it could be seen as a branch of the geometric deep learning, perhaps?
Let me try to make it more clear what Vinicius said and give you more details. Actually, what I would say is that what we are studying here is deep learning for geometry.
Okay.
Right. But what is being called geometric deep learning in the community is something totally different that is related to the geometry of the neural network. Because if you think about it, in that sense, I mean, like what we are doing can benefit from geometric deep learning. But in fact, it's funny because the people that are proposing this theory of geometric deep learning actually have not addressed implicit representation.
Yes,
they actually are using that for explicit representation.
Yes.
But the basic idea is that you have, a function space. And what you are trying to learn is manifolds in this function space.
Yeah.
So the function space has an underlying metric, underlying geometry. The manifold also has the underlying metric and geometry. And what makes you learn fast in a stable way is when you have certain properties with the operators that are behind the mathematical model that this neural network is trying to learn, right? So for instance, convolutional networks, they are very successful because they use a convolution operator, which gives translation invariance, right? And we have seen here, like in some of the works for implicit surfaces, when they go from global to local and they use convolution, that improves a lot, right? And we have seen why when you do the spectral mapping, that improves, because when you do the spectral mapping, basically you get like a translation invariance too. So what these authors that are proposing geometric deep learning have done is that for every kind of network architecture, let's say you may have collections of points, right, or different sets, right, or you may have like sequences, or you may have grids, or you can have images. Different settings, you have certain operators that needs to be preserved, right? You need to preserve like some symmetries, you need to preserve like some properties so that the network is going to learn the right thing, right? And this is a key for doing machine learning in an effective way. And they sort of combine, all this inspiration from the basic, properties that are used in geometry, geometric aspects of invariants of spaces and topology and things like that, right? And it's a very beautiful theory. And that once you understand, then you can benefit in applying that theory in practice. But there's a step from going from one to the other. And but encourage everyone to look in the web, geometric deep learning. There are courses. This group is actually writing a book that I think is going to be one of the important books in the area.
Okay.
Yeah, and another note is about non-Euclidean geometry in this aspect is there is one author Yaron Lippmann, that is working with that. He has a very recent results about apply those concepts of, for example, in Riemann geometry. He has a few works that have been talking about that. They are recent, so we have not presented them here, but if you want to research about it, you probably need to follow his work, Yaron Lippmann.
Okay.
He is the author of IGR, IGR with which was presented by Luis Schimmer in this presentation.
Okay. Okay. So I think we have finished here. I'd like once more to thank the authors for this tutorial and to thank all the participants, all the attendees in this tutorial too. Thank you very much. See you all in the SIBGRAPI.
Okay, great. Thank you.
Bye. Thank you. Bye, everyone.